Hello everyone and welcome to the first video of the third lecture of the course on metric spaces. In the first lecture we considered the plane, which is R2 with points P of coordinates xp, yp, and we defined the distance on the plane between such a point P and a point Q of coordinates xq, yq as the square root of xq minus xp squared plus yq minus yp squared. And we remarked that essentially by definition the distance between p and q, if we draw the picture in which we represent the y-axis and the x-axis and we take the points p and q, then their distance represents exactly the length of the segment connecting them. What we want to do now is to upgrade this example to 3 dimensions. Namely, instead of considering the plane, we will consider R3, which is the 3-dimensional space in which we live in, and it has, for every point, coordinates xp, yp, zp, which are exactly the x-coordinate, the y-coordinate, and the z-coordinate. So if we were to draw R3, we would have to draw 3 axes, which are the x, the y, and the z axis. So x, y, and z. And P would be a point here with exactly 3 coordinates, which are the z coordinate, and when we take its projection on the plane xy, the y coordinate and the x coordinate. Okay, so for example, a point in R3 in the space might be the point 1, 1, 1, which just means that it has x, y, and z coordinates equal to 1. What we want to do now is to define a metric or a distance on R3, which is just a generalization of the metric we had in R2. How do we do this? Well, we consider a point Q of coordinates xq, yq, zq, and we define the distance between P and Q to be the square root of xq minus xp squared plus yq minus yp squared plus zq minus zp squared. This is a distance on R3, on the space, and we can easily see that once more, almost by definition, the distance between P and Q, which I denote dpq, is equal to the length of the segment connecting P and Q. This time, of course, in the space. So if I drew the point Q here, then I would have to draw the segment connecting P with Q, and the distance between P and Q would exactly be the length of this segment here. Let's do an example. So we take P as before, 1, 1, 1, and we consider Q equal to 2, 3, 4. Then the distance between P and Q, using the formula we wrote here, is given by the square root of 2 minus 1, which is 1 squared, plus 3 minus 1, which is 2 squared, plus 4 minus 1, which is 3 squared, which means the square root of 1 plus 4 plus 9, which is equal to the square root of 14. This was an easy example, and you will have the chance to try some other examples of this distance in the exercises. What we want to do now is to use this distance to define a distance on the sphere. The first thing we have to do then is to define what's the sphere. The sphere for us will be given by the set of points P of coordinates xp, yp, zp, such that xp squared plus yp squared plus zp squared is equal to 1. If you remember how you define a ball in a metric space, you might notice some similarity between this definition and the definition of a ball centered at the origin with radius 1. Indeed, there is a relation between these two notions you will have the chance to look at in the exercises. Basically, the points of the sphere are the boundary of the ball centered at the origin of radius 1. If we wanted to draw the sphere, then we would have to draw the three axes x, y, and z, and then the sphere would be given by this set of points, where the intersection between the axes and the sphere are given by 1, 0, 0 for the x-axis, 0, 1, 0 for the y-axis, and 0, 0, 1 for the z-axis. What we want to do is to define a distance on the sphere, and the way we do this is the following. If P and Q are points in the sphere, then we say that the distance on the sphere between the points P and Q is equal to the standard distance between P and Q as points in R3. So it's once more given by the square root of xq minus xp squared plus yq minus yp squared plus zq minus zp squared. What does this mean geometrically? Well, it means that if you take a point P here on the sphere and a point Q here on the sphere, then to compute the distance between them, you just take the segment that goes from P to Q and it goes inside the sphere, and you compute the length of this segment. So, for example, if you wanted to take P equal to 1, 0, 0 and Q equal to 0, 1, 0, then the distance on the sphere between P and Q would be given by the square root of 1 plus 1, which is equal to the square root of 2. This definition tells us that everything we compute on the sphere is equal to the result we would obtain if we computed that number in the space, simply because we define the distance on the sphere to be the one of the space computed only on the points which belong to the sphere. In particular, even if you were to draw a curve, for example this curve, which lies completely on the sphere, then the length of this curve wouldn't depend whether you compute it as the length of a curve on the sphere or the length of a curve in the space, simply because we define the distance on the sphere restricting the one on the space, where by restricting I mean that we're computing the distance only on the points which belong to the sphere, but the number we associate to every 2 points is exactly the same we associate to those points when we consider them in the space. This is one of the 2 examples of distances we will see on the sphere, and the next example will come in the next video, where we define the distance on the sphere which comes from measuring arc length. So I'll see you in the next video.